Hey, finally, we're going to do this post equivalence point calculation. And just like in those previous two calculations, this is going to be slightly different. Okay, there is going to be some subtle differences. And now, of course, I did not do a very good job of leaving myself enough room, but we're going to try. So I'm going to just draw like a little line right here. Okay, so now we'll say number 3. And we're going to start this third calculation off in the same way that we did it with this before and after. So that's going to be my acetic acid plus my hydroxide goes on to make acetate plus water. So here now, once again, we're starting with the same number of moles of acetic acid. I'm going to take a little bit of a shortcut, okay? So we're doing this problem 3, 30 mils. So now we should recognize our new solution volume is 50 milliliters. And hopefully you can see the trend now in our molarity calculation. So on problem 1, our hydroxide was 1 millimole. On problem 2, with the 20 mils, our hydroxide was 2 millimole. And now on problem 3, with the 30 mils, our hydroxide is going to be 3 millimole. So you can actually see now we're going to have excess hydroxide, okay? And so that means now the acetic acid is the limiting reagent. And so all of it is consumed to 0. But now I have leftover hydroxide. And we also recognize that I'm going to have some acetate that's created as well, right? So this creates about 0.02 moles of acetate. However, because I have leftover hydroxide in this post-equivalence point calculation, none of this matters. That leftover hydroxide is going to dominate the pH relative to whatever acetate I have left over, okay? And so now this simply means that I have 0.00100 moles of OH minus. My new solution volume was 50 milliliters, so I'm going to convert that into a molarity by dividing by the 0.0500 liters, right? That was my 50 mils. So when you do that, that is 0.0200 molar OH minus, okay? And that, like I said, that dominates the pH. So if I have 0.02 molar and I take the log of that, now that gives me a pOH of 1.70. And I can just now add 14 to that, and that gives me my pH of 12.30, and that is my final answer. So you can see this post-equivalence when you have leftover hydroxide, or really to say leftover titrant, it just becomes a very straightforward calculation because we assume that that leftover conjugate base is not going to be significant compared to the amount of hydroxide. And if we look at that pH 12.3 and we look at our curve, right? If you notice here, look, maybe there's 12.3, okay? At a certain point, it hits that pH and it's kind of just staying at and around that vicinity because now the pH, let's say from about right here on, is really only dependent upon how much hydroxide I've added because the hydroxide overwhelms any leftover conjugate base that I'm going to have. Okay, so now I've got a whole other set of problems for you. And now these are based on slide 17. And now this is the calculation to do the base weak base titrant being added to a strong acid, but I'm not going to do these in my recorded videos. We'll do these in lecture, and you can also certainly practice these on your own. Okay, folks, just one last mini video for this chapter.